Welcome back to ECE 320A. We're a day or two removed from our break. I think that's, actually I should applaud the people that are here, right, in attendance. This is pretty good attendance for a day before. Extra credit, I knew that was coming. Some announcements. Watch for homeworks. I really don't want to post one before we've had enough background material to allow you to work these problems. We will be talking about Bode plots, which really are in the appendix, and I think it is Appendix E. Today we'll talk about, or we'll try to do the introduction, and we'll then look at the process more maybe in detail when we talk about sketching these Bode plots with more terms. But as a reminder, the final exam is not on a Tuesday or a Thursday. It's on a Friday. So if you're used to doing circuits only on Tuesday, Thursday, you might want to try a Friday, a Black Friday edition of 320 and start doing some problems on a Friday. Yes. It will be in this room, and it will be from 1 o'clock to 3 o'clock. It will be a 2-hour final, and that's Friday the 11th of December. Pardon? I cannot adjust the dates or the times of the final. So it's mandatory, the final. All right, let's get into Bode plots. And when you hear Bode plots, you might be thinking frequency response, meaning what are these curves, or what's this system, how does it behave as a function of frequency? And when I say Bode plot or Bode plots, I'm really speaking of two different curves. One is a magnitude curve relative to frequency or with respect to frequency, and the other is the phase with respect to frequency. And if we have that plotted for all frequency values, you can then use that information to immediately write down a sinusoidal steady state response if I give you a specific frequency. You can simply go to that frequency on the two plots, find the magnitude, find the phase, and then, well, the magnitude, it's indirectly given to you because it's going to be expressed in decibels, but you can then back out the actual magnitude and use that to derive the sinusoidal steady state output from that system that produced that particular Bode plot. Let's start, when we're talking about Bode plots, with something that you hopefully can connect with, a triangle, a three-sided object. And now I'm putting some facial features on that triangle. One is an eyebrow and one's, I don't know what a plus sign, what would that be? A nose, maybe? All right, sorry. Let's ground that non-inverting terminal. Then on the inverting terminal, let's insert, ouch, a feedback of a parallel combination of a capacitor and a resistor. And now that I have two resistors, let me label those as subscript 1 and subscript 2. Here's the input, V sub I of t, and maybe we even have a specific load resistance R sub L, and now we might label that output voltage V sub 0. When you see that circuit, do you think any particular behavior without even doing any kind of analysis? If not, then let's do some analysis, but this is actually a low-pass filter. What's the order of that low-pass filter, if you had to guess? First order because we have one energy storage device. And what I'm not showing are the power supplies that are energizing that op-amp. This is an active circuit versus the passive circuits that we have played with before. This actually now is an active circuit. We can make this in terms of intuition maybe a little easier to think about if we just lump those impedance elements into one impedance parameter, let's say capital Z sub F, where now Z sub F, how do I compute that impedance in the feedback path? And where is that feedback path going relative to the op-amp input terminals? Is this positive feedback? Is it negative feedback? It's now negative feedback. It's now trying to force those input terminals to an opposite direction to what the output is doing. And that's giving us this negative correction or negative feedback. Sub F, that impedance is just the parallel combination of R sub 2 and the impedance of the capacitor. So we could say, oh, that's R2 in parallel with 1 over SC. So that now we have R sub 2 times the impedance of the capacitor, 1 over SC, times their sum. And now we have SC in the denominator of both the numerator and the denominator. If we get a common denominator in the denominator and the numerator, we can cancel that SC and end up with an R sub 2 over S R sub 2C plus 1. And now we have this frequency-dependent impedance, just like a capacitor and an inductor are frequency-dependent impedances, but now it has a little different structure than just an impedance or a capacitor. If we now want to find the relationship between the input and the output, and a lot of times I will say, maybe label these in the time domain, and I will ask you for a transfer function. I didn't think that that would be confusing, but some people on the exam said, oh, since you're asking for the time domain, then I'm going to give it to you in t. And they were looking at the ratio of v sub 0 of t over v sub I of t. And that's not the way we want to think. If I say transfer function, we're immediately in the frequency domain, and now we're thinking about capital V sub 0 of S and capital V sub I of S, even if I ask about the transfer function between point A and point B. I hope that becomes clear by the final. If we now want to find the transfer function of this circuit, I now want the transfer function between the input V sub I and the output V sub O. What kind of equations are you seeing or thinking you might write for this circuit? So now I hope you're starting to maybe think, well, maybe I could write node voltage at that particular node, V sub n, at the inverting terminal of the op-amp, where relative to that term, or that node, I have a current going to the left, a current going to the right, and a current, theoretically, going into that inverting terminal. But we know that that's 0, and so really we just have to add up the current going left to the current going right, and those equal 0, KCL equation. If we write a KCL at node V sub n, the current going to the left in terms of, let's say, capital V sub n minus capital V sub I over R sub 1, that's the current going to the left. Does everybody see that current? And if that's what's going left, something similar is going right, where now we have V sub n minus V sub 0. And all of these, now that I made a big deal about being in the frequency domain, maybe I should emphasize that here by making these arguments of S. And those two currents now sum to 0. This simplifies considerably because what do we know about capital V sub n? Since this is a negative feedback, we now have this basically virtual connection between the inverting and non-inverting. Their voltage separation is 0. And the non-inverting terminal is connected to ground, or the reference terminal in this case. So capital V sub n is 0. And we can now find, or this now allows us to say, V sub 0 of S over Z sub F is equal to minus V sub I of S over R sub 1. And we can now solve that for our transfer function of interest. But we've already derived the formula for that impedance, capital Z sub F, which allows us now, let's go ahead and push that R sub 1 in the denominator here into the numerator of that fractional expression for Z sub F, and we have minus R sub 2 over that R sub 1 in the numerator, and then we have S R sub 2C plus 1. And now, if that circuit initially didn't look like a low-pass filter, I hope that it does now. Which means that this particular circuit favors low frequencies. If you looked at the very low frequency, let's say DC, S is equal to 0, that's the smallest that denominator term is ever going to be, which is 1. If you start increasing S, and really we're going to be replacing S with j omega, you're increasing j omega, now that magnitude of that term is getting bigger, so you're just continuing to get smaller as the frequency grows. And what does the frequency response of that low-pass filter look like? Just in an approximation sense. Or, what do I want to say? In a very general sense, could you just say, oh, the magnitude is going to be flat, and then it's going to go down? Very basic sense, and that is only going to break once because it's first order. And where is it breaking? What is that point called? The break frequency. Or you might hear it called the cutoff frequency. And what is this? That shouldn't be lower at the low end. I hope you realize that's just a typographical error of the drawer. This is our maximum value in that frequency response. And where does that occur? Where is the smallest value of our denominator happening? For what frequency is our denominator the smallest? At DC. So this is the transfer function at DC, or we're now looking at H of 0. And in fact, the actual curve, if you were going, went into the lab, it would be decreasing, and it would be then a certain distance below that approximated kink or break, and we're going to show what that value is now in terms of what is this distance between the approximate curve. This is the approximate curve, the curve in blue, or what we will call the straight line approximation. And that's what you would sketch for an interviewer if they said, what's the frequency response of this system? You could simply just pull out a piece of paper or a napkin, whatever you have available, or your phone, I guess, if the display is working. And draw what you need on that. This is the actual. And this is now the magnitude in dB. You said it's a first order. Where is our pole? It's the value of S where that denominator vanishes. That's how we've been defining it. We now know that we have S R sub 2C plus 1 equaling 0. S is a frequency, so what do we know that term that scales frequency must equal? So frequency is 1 over seconds, let's say, so this must be some time, and that's actually our time constant, tau, RC, R sub 2C. If we solve that for S, that is our cutoff frequency or the break frequency. And for this particular circuit, we can compute the DC gain. And now that's going to depend on the ratios of those resistors, the feedback resistor over the input resistor, and that minus sign, that's just inverting. If you had a sinusoid, it would just invert that sinusoid, but the magnitude would be adjusted by this ratio of R sub 2 to R sub 1. What's the magnitude of this transfer function at the cutoff frequency? That's what we're interested in right now, is this particular point right there. That's what we will compute. And we just said that this particular point is omega sub c in frequency. We want to know what is the magnitude at that point. We are now looking at the magnitude of h of j omega when omega is equal to omega c, which is this 1 over R sub 2c. So now I'm looking at the magnitude. I'm throwing away the negative sign or the sign change, and I want the magnitude of the denominator. That was j omega, and the omega is 1 over R sub 2c. But in this case, it was j omega times r sub 2c, so we have an r sub 2c plus 1. I hope now that you see that that frequency of 1 over r sub 2c cancels the r sub 2c, or the time constant, and now we have the magnitude of 1 plus j. And if you're looking at that in the complex plane, we're now going over 1 and up j. We are now looking at the length of that line. Or the hypotenuse of a right triangle that has horizontal distance of 1 and vertical distance of 1. Now we have this square root of 2, so that we now have this difference in magnitude between the low frequency gain of that circuit and the gain at cutoff. It's down by this factor of square root of 2, or 1 over the square root of 2. That's the magnitude of that point at the cutoff. And if you wanted to look at that in terms of dB, you could say, well, I'm curious what that factor produces, and this is where that magic number comes from, that minus 3 dB. But 20 log of 1 over the square root of 2, we can say, okay, that's 20 times the log. And now that's the beauty of logs. We can add and subtract those when we're multiplying and dividing. Here we are dividing 1 or the square root of 2 into 1. We then have the log of 1 minus the log of the square root of 2. What's the log of 1? That's 0. Minus the log of 2 to the 1/2. And now if I pull that negative sign out in front and pull the 1/2 out in front, which is the exponent on that argument of the log, this is now why it's nice to know all of those logarithms just in your head. When you say log of 2, oh, that's approximately 0.3. You just know that, right? So this piece right here is approximately 0.3, so that we now have minus 20. Let's go ahead and multiply 20 and 2, or divide 20 by 2, so that we have minus 10 times the log of 2. And that's why you might hear people talk about the 3 dB point or the 3 dB frequency. That's now when you are down, or that's where that cutoff frequency is coming from. It's this square root of 2 difference, or this reduction by the square root of 2 from your baseline or from your low pass magnitude. And you know quite a bit about that. What we haven't talked about today is how fast this is falling in terms of how many dB per decade. And what's a decade? 10, or a factor of 10. Or we could talk about how fast it's going down in an octave, which is a factor of 2. For a first order piece, it's 20 dB per decade, or 6 dB per octave. Let's now look at that in maybe a more generic example. Suppose that now you are given a transfer function that somebody says is k over tau s plus 1. And we are going to make a big deal about how we represent our transfer functions when we're performing Bode plots. This particular representation is not in pole zero form. This is in time constant form. And the reason that we're calling it time constant form is we've now normalized the constant to be 1. And this allows all of the gains of all of our factors to be absorbed into one gain piece, and then we can simply start examining the factors in a more general or consistent manner. So what we want to do now is develop a procedure for sketching the magnitude as a function of frequency and the phase or angle of all of these expressions. If we simply looked at the magnitude of this, let's say in dB, then we are looking at 20 times the log of the magnitude. And now for the frequency response, we are actually walking up the imaginary axis in our S-plane and evaluating the magnitude and phase at each of those frequencies omega. We don't want to do that piece by piece by piece for an infinite number of omegas. With your calculator or otherwise, you want to have some strategies for sketching these a little bit more quickly. Now that I have it written that way, I can say, okay, that's 20 times the log of the magnitude of k, and now what do I want to say? Now I have j omega tau plus 1. But what did we say we could do when we have the log of a fraction or of a product? That's why we are looking at these in dB, so if we put in additional terms, we can just add in that individual contribution. Here we simply have two terms. We're going to have a constant term, and then we have the denominator term, which is a first order factor. So now when I say in this particular transfer function, k over tau s plus 1, I might say, oh, we have two terms. Do you see where I have the two terms due to the magnitude? I have a term due to the constant, and I have a term due to the pole factor. And we can do the same breaking up into factors if we looked at the phase of h of j omega. In this case, I'm looking at the phase of h of j omega, which is now the phase of k over j omega tau plus 1. Now the phase, the numerator terms add, the denominator terms subtract, so that now I have the phase of the numerator minus the phase from my first order denominator piece. And again, I have two terms that I need to worry about from this particular transfer function that I started with. And so I may just say, okay, we have two terms. Let's look at those two terms. And that's what I'm going to do now. Is it clear where those two terms are coming from? We have magnitude separated into two terms and the phase separated. Let's now look at those two terms individually. We have a gain term, which is just the gain k, and we have a linear pole factor term. That's this tau s plus 1, and the linear is because I just have s to the first power. And since it's in the denominator, I'll go ahead and emphasize that and say that's this linear term, tau s plus 1 raised to the minus 1. This is now because that was a pole factor. And what we want to do is look at those individually so that we can then, if we now have a transfer function that has 3 numerator pieces and 5 denominator pieces, you know the strategy for each of those pieces. You just have to do this 8 times and put all of those 8 pieces onto your magnitude plot and phase plot. But they will all be the same process in terms of sketching. And then you just have to add all of those pieces together. So let's look at magnitude and phase as a function of omega, or frequency, for each term. For our gain term, if we looked at the magnitude, that's now 20 times the log, and that's log base 10, that's the magnitude of k, and it's that expression. Is k a function of frequency? It wasn't, was it? K in our case was just this R2 over R1. That was just a constant. So this is just going to produce one number for a given K. If K in our particular case, let's say this is, so now we're going to sketch all of this as a function of log of frequency, because that allows us to put a lot more frequency information in the same, let's say, horizontal length of our page or paper. Now we would have, let's say, 10 to the 0, which is 1 radian per second. Then an equal spacing from that would be 10 to the 1, 10 to the 2. I'm assuming everyone, in addition to your 64 color box of crayons and your ruler and your dividers, your protractor, you also purchased some semi-log graph paper. 5 cycle. 5 cycle just means that you have 5 of these decades represented on that piece of paper. We used to have to buy that at the bookstore. May I have a package of 5 cycle log paper, semi-log paper. Semi-log because the horizontal or the vertical is normal units. It's not logarithmic. You could have, I need log paper, or I need semi-log paper, or I need engineering tablet, which is what? Rectangular grid, right? They're blocks. They don't have these interesting divisions that are logarithmic. Where is 2 on this plot? If somebody keys in log base 10 of 2, what are they going to get? 0.3. So that means that 2 is 30% of the distance between 1 and 10. 2 in this case, if this is 30%, that would be 2. You put in, oh, what's the log of 5? Somebody help me out. What is the log of 5? 0.69, so it's 0.7. So now 5 is 70% of the distance, so this is now 5. Now you can see if you're stuck with engineering paper, you can actually make that logarithmic by just calculating what's the log of 2, what's the log of 3, what's the log of 5, and once you have 2, 5, and maybe 8, you have pretty good range on those spacings between 1 and 10, and those same spacings, where's 20? Let's see, do I have a 20? No, somebody's been in my wallet, haven't they? I don't have a 20, but where's 20 on this paper? 30% of the distance between 10 and 100. Are you getting this? Okay. So now here's 20. What was that about? Oh. So now where do I put K? What is this picture going to look like if I'm plotting the gain term with respect to frequency? And this line is typically 0 dB, which in absolute terms is how big of a number. What log of x will give you 0? 1. Right? So this is 1. That means if this is the gain, and it's a value of 1, that means you put in a magnitude of 6, you're getting out a magnitude of 6. The gain is 1, 0 dB. K was 10. Capital K, let's say, is 10. What's that in dB? Log of 10. Really? Base 10? Isn't that 1? Because log of 2 was 0.3, so log of 5 was 0.7. Log of 10 is 1. So now we just scale 1 by 20, and now if we had a gain of K equal to 10, this would be 20 dB, and you would just draw that with your ruler, just a flat line. If your gain K was 100, then where are you? Now you have log of 100 is 2, so now that's at 40 dB. If K was 0.1, 10 to the minus 1, do you see how this is working? I'm giving you nice divisions of the gain K, or magnitudes for K, but if K was 5, then what would it be? If you told me log of 5 was 0.7, then I have 20 times 0.7, or 14. I would be somewhere between 0 and 20 at 14 dB. And that's how you would sketch the gain term in this Bode plot. What's the phase of K? So we have two plots to sketch. A magnitude plot with respect to frequency. So let's say we're done with that. Magnitude. And now we want to sketch the phase. And you're going, phase? Okay, there's a trick here maybe, or just a subtlety. This could actually have two values. So it's either positive or negative, isn't it, our gain? If it's positive, what's the phase of a positive number? So that now you're looking at, let's say this is our S-plane, and this is the real part of S, and this is the imaginary. You can always sketch these to try to gain some. Now let's say K is over there, it's positive. What's the angle from the horizontal axis to that red dot? 0. I don't have to change my gaze at all. That's 0. But if it was negative, then I actually have to turn 180 degrees. And typically, Since we think of things happening later in the output than at the input, we usually get to that same point by going a minus 180. They're equal, but I like to just say if it's negative, let's just assign it an angle of minus 180 degrees. If it's positive, it's 0. And it's that value for all frequencies. Again, this is pretty easy to sketch. Here is our horizontal axis. This might be 0 degrees, and this is what K would be. Or that's the phase due to that constant term if K is greater than or equal to 0. If K is negative, now it's this curve, which is that's supposed to be a flat line equaling minus 180 for all frequencies. Constant terms should be a piece of cake to sketch. Once you've found the constant in that transfer function, once you've converted that transfer function to time constant form, you now have the constant, K. Take log of that base 10, scale it by 20, and you've got the constant value in magnitude. The phase depends on the sign. Let's look at the linear factor. In general, it looks like tau s plus 1, and that could be in the numerator or the denominator, and as a function of, or the frequency response is found by replacing s by walking along the imaginary axis, or s is equal to j omega. This is now j omega tau plus 1. What's the magnitude of this piece going to look like? By definition, that's just 20 times the log base 10 of the magnitude of j omega tau plus 1. And here's where I like to invoke Goldilocks. Dr. Tharp, this is electrical and computer engineering. Yeah, but let's have story time. So story time with Goldilocks. What was she doing when she went into the house? What was always happening? It was too hot, too cold, or just right. It was too big, too small, or just right. So we're going to look at extremes. With respect to this term, we want to look at omegas that are really big, omegas that are really small, and an omega that's kind of right in the center. That's what I'm meaning by treat this like we might treat Goldilocks, or thinking Goldilocks. Now if somebody is interviewing you and they say, oh, so can you sketch the Bode plot? Oh, sure. This reminds me of a story, Goldilocks. So you might not want to carry that out vocally, but it might be a way to key into what you're trying to do. So what we're trying to do here is find a way to sort of quickly approximate the sketch of this term. We don't want to do it point by point for every omega, from DC up to whatever frequency. We are going to look at extremes. For starters, let's look at something small. Let's say and now we really just have two pieces. We have a real part and an imaginary part. It's 1 plus j something. So and that real part, that's why we like it. We've normalized that to equal 1. So that makes it easy. All of the action is occurring in that imaginary part of this expression. So we could say, what if omega tau is much less than 1? Do you see why I might want to do that? then this really simplifies that expression. If omega tau is much less than 1, then I have 1 plus j something that's negligible. So I basically have 1. And I can find the magnitude of 1. That's pretty easy. And that's why I'm doing this. But in this case, I now have, if I solved that for omega, now I have omega much less than 1 over tau. Ooh, what's 1 over tau? Break frequency, isn't it? And what are we assuming is much less than? Here's where we get into the approximations. Let's just agree that to be much less than the break frequency, let's just agree that that means we are a decade below the break frequencies, where this approximation is okay. And that's 1/10 of omega c. That's what we're considering to be too small, or very, very small. So now we're looking at omega values much less than 1 over tau, and this is, as we said, that 1 over tau is actually our pole location, and tau is the pole's time constant. And at this extreme, then j omega tau plus 1, when omega is, let's say, less than 0.1 times the break, or a decade before the break frequency, we can approximate that complex expression to just be 1. And now we have what the magnitude looks like as a function of frequency for small frequencies, or small omegas. Under this constraint of frequencies being less than or a decade below the break frequency, we are approximating 1 plus j omega tau by 1. We now have, this is approximately 20 times the log of 1, which is 0 dB. So now we are flat at 0 dB for this linear factor. For both numerators, or zero factors, and pole factors, we're flat until we get close to the break frequency. And that's what we saw in our approximation anyway. Now, if we look at another extreme, where omega tau is much bigger than 1, or omega is much bigger than 1 over tau, which again is our omega c. And what do you think we mean by omega much larger than the break frequency? What do you think we're going to make for that frequency, or frequencies beyond a particular spot? If much smaller was a decade before, much larger must be a decade after. So this is now 10 omega c. If we now have j omega tau plus 1 under the condition that omega is 10 times the break frequency, then what do we know about that imaginary part of this complex number? It's 10 times the size of 1, isn't it? So this now we can approximate with just the imaginary part of this. This is when omega is greater than 10 omega c. That's the approximation. So that now, if we looked at the magnitude piece in that range of frequencies, we now are saying, oh, we can approximate 20 log of that linear factor by just 20 log of j omega tau. But remember what tau was? Or 1 over tau was omega c, so tau is 1 over omega c. And if that's the case, what's the magnitude of j? If you were in the complex plane and I said, go to j, go directly to j, do not cross go, where would you go? Where's my horizontal axis? Let's say it's south. So then I would turn 90 degrees, wouldn't I, and go up 1. So what's the magnitude of j? What's the length of that distance? 1. So I can drop that j from my magnitude and just consider positive frequencies so that now I have, whoops, can't throw away the log. You guys are probably sawing logs. So I can't throw them away, right? We now have log of omega over omega c. Is it the absolute value of that? Now I'm saying let's consider all of these frequencies to be positive. Omega c is a positive number, and omega, we're just going from DC up to positive values. So we're no longer worried about the absolute value. And now that I have a ratio, what can I do with that? Because we're playing with logs. Now I can break that into two pieces. I have 20 times the log of omega minus 20 times the log of omega c. And do you remember when we were sketching the constant term? What was our horizontal unit, or what was our axis that we were using? What was our independent variable? How did we label that independent variable? Not giving any hints at all. I just sort of under bracketed something that you might, wasn't this our independent variable? Was log of omega. So now we have 20 log of omega. That's 20x in a way of thinking. And this piece, what is omega c? That's a constant value once we've found that break frequency. This is just a number. And before we go too far, we can actually find the sweet spot, which is what? Between too low and too high. If I looked at this and said, what happens when the frequency is equal to omega c? What happens to our magnitude? So this one now gives us 0 dB. So at the limit, if we went a little bit smaller than 10 omega c and went all the way back to omega, then we would be at 0 dB. And what did we start with for low frequencies? That was giving us 0 dB. So we find the intersection of these two lines. If we look at this, what I'm trying to suggest is this is our magnitude, 20x plus a constant. Does that look like a straight line where x is our independent variable? Our magnitude now looks like 20x plus B. Mx plus B. And because we actually had a pole factor, which I didn't account for until now, our pole factor we could think of as j omega tau plus 1 to the minus 1. That's in the basement or downstairs, or that's in the denominator. And so now, if we were looking at that, we have 20 times the log of j omega tau plus 1 to the minus 1. This is now minus 20 times the log of that same expression that we were just talking about. And we know how to approximate that. For small omega, it's 0. For big omega, it's varying with a slope of either plus 20 per dB or per decade or minus 20 per decade. It's this 20x. So that now for this straight line approximation of a linear factor, what I'm hoping you have an appreciation for now is if this is my independent variable, log of omega, and I want you to plot the magnitude in dB of the linear factor, where do I start on the left for low frequencies? 0. And when is this flat line at 0 going to intersect with the sloping line? Right when Goldilocks is happy. Right at the sweet spot. And what's the sweet spot? When it's just right, which is when omega is equal to omega c, right at the break frequency. So we would go and continue flat until omega c, we would be at 0 dB. And then if it's a pole factor, we are going to be sloping at minus 20 dB per decade. Is it clear where, and now all you have to know is you just need to factor, first you have to put all of your factors into time constant form, find what your break frequency is, and do you see how easy these magnitude plots are? It's just 0 dB until the break frequency, and then it starts going down. If you had a second one, then that would have a different omega c or break frequency, and you would sketch that to that different frequency and then go down. And we'll show how to put all of those pieces together. But this is just one. Let's now look at the phase. If now somebody was playing their stereo and they had that for their graphic equalizer, and omega c was, let's say, 10 hertz, what would you be hearing? If this was your equalizer that was filtering all the waveforms or all of the signals coming out of your stereo, and the break frequency was 10 hertz, now that's F sub C, what would you be hearing? Probably wouldn't be hearing a whole lot. What do our ears hear? Our frequency response, if we're lucky, is 20 hertz to 20,000 hertz. That's if you're young and haven't been damaging your hearing. Mine's probably more like, let's not go there. But it rolls off with age, with frequency. So I can probably only hear about 12,000 hertz. I do this experiment in the summer. Yes?
Do you ever wanted to, like, make a circuit? Do you ever start with, like,
Yes, so what we want to do, the question was, can we start with a transfer function and then build a circuit from that? And the answer is yes. Stay tuned. Don't eat too much turkey. Come back from your break, and we will discover how you can do that. And that's where we will start. We will learn, well, you already know how to do that, right? If somebody gave you, wow, where were we? That, you could now build that with this. So you now know how to build a first-order low-pass filter. We will then find a second-order filter, and now you can break everything up into second-order pieces and first-order pieces. Fifth-order filter, it's now 2 second orders and a first order, and you put those together. So we will learn how to do that after the break. Is that okay? Now, let's worry about Goldilocks and phase. That's j omega. Now we have a linear term, and we want to think about its phase. And let's use these extremes. So the first extreme is when the imaginary part is much less than the real part. Or that's when omega much less than 1 over tau, which is this break frequency, omega c. If that's the case, what's the phase of that piece? What does j omega tau plus 1 equal when omega tau is much less than 1? So now I would just walk in the S-plane. I would go over 1, and how far up am I going to go? If I turn left, it's very small, so I'll just kind of not go anywhere. And what's the angle to get me to where I'm standing? So this becomes the angle of 1, which is 0 degrees. Does everybody see that? What about the other extreme? Now when omega tau is much bigger than 1, or omega is much bigger than the break frequency, now the angle of j omega tau plus 1, now what happens? Now I go over 1, I go over 1, and then what do? I go up quite far, don't I? What's the angle from the origin to here? I don't have my glasses on, so I can't see, but where are we? Where was I? I'll borrow those crutches. Thank you. Where was I? At an angle. What was my angle? This now is essentially j omega tau, right? So now I basically only have imaginary component. And I measure all of my angles relative to the horizontal real axis going off in the positive direction. I now need to turn 90 degrees. So this is 90 degrees. That's if the j omega tau plus 1 term is where? That's in the numerator. If it was in the denominator, I would subtract this 90-degree contribution. So if I now have a pole factor, that's linear, how do I sketch the phase plot? There's log of omega, and what 3 points am I interested in? And I could say, okay, here I'm pinning that in or down on the omega axis. That's my break frequency. Relative to that, Goldilocks has 2 extremes. One that's a decade beyond that, and one that's a decade below that. What's the angle? So this is now the angle of j omega plus 1, and let's say that that's a pole factor. So it's minus 1. When omega is much less than when omega is much less than omega c, below a 0.1 omega c, what's the angle? That's roughly 1, and that has an angle of 0, doesn't it? So now we're right here. If we're a decade beyond omega c, where are we approximating that to be in terms of angle? 90, but since it's in the denominator, it's now minus 90. Now, if we went back to this, and I said, what happens at the sweet spot? Which is when j omega over omega c plus 1, and we want omega to equal omega c, we now have 1 plus j. And I'm not going to get hurt doing this, am I? I go over 1 and up 1. What's the angle? 45 degrees. And since it's in the denominator, it's minus 45, which happens to be exactly between 0 and minus 90. Here's 0 degrees, and then I just connect these dots. That's supposed to go right through, and that's supposed to end up right at minus 90. No kinks in that. Okay, so that's why you learn not to draw dots and lines, but this is now supposed to be minus 45. Ooh, that looks pretty. Not pretty, but kind of not right. So let's see. That's why you hope your display is broken, so it would hide these imperfections that I'm having trouble with. There. Well, ooh, it looks okay when I'm laying down on the desk, but all right, so there's our phase curve. Are we ready to put all these pieces together? What was our gain, or what was our phase for a constant? If it was a positive constant, what did we have? 0. So this would be the phase response. So now if we put in a frequency, an excitation right at the break frequency, what's going to happen? And let's say that our gain was 1. So K was 1. I'm just kind of, you've had your Dramamine, right? And if you've had plenty of turkey, it won't matter, right? If you're watching this after the fact. We would be at 3 dB down, and what would be our angle if we were at the break frequency? Minus 45. So now you know how that sinusoid output is going to be affected by going through that low-pass filter with a DC gain of 1, a cutoff frequency of something, but we're now right at that cutoff frequency, and we'd be down by a factor of the square root of 2. What we want to do is start to do this for a more involved transfer function. So, while you are participating in your break activities, you can be thinking about how you would sketch the Bode plot of that. So this now is what we will be trying to digest when we get back, speaking of the break. But what do we have differently? We have already covered a linear factor and a gain. We haven't worried about a quadratic factor, and we haven't worried about a pole or a zero at the origin. If we can figure those out, we've got everything figured out for how to do Bode plots, and that's where we will pick up after the break.